All right, so time to get started. Remind you, in chapter 4, we've been talking about axial deformation. And the last thing we did yesterday was we worked some examples of what we call statically indeterminate problems. And today we're going to turn our focus to looking at what effects temperature change has on materials, structures, etc. Anybody got a question about something they want to ask before we get started? Alrighty then. And again, the topic of the day you'll find in section 4.6 in your book. And the title of this section in the book is called Thermal Stress, which is a little bit, the name's a little bit misleading. I see the name thermal stress. I'm thinking this is stress caused by temperature, and it's more of an indirect effect that causes the stress. But we'll talk a little bit more about that in just a minute. But typically, if the temperature changes, then the material is going to change shape. It's either going to expand and get bigger, or it's going to contract and get smaller. And for the most part, I'm not going to say all, but the vast majority of materials out there, if the temperature increases, that's going to cause an expansion. The material is going to enlarge and it's going to get bigger. And if the opposite happens, if the temperature decreases, we're going to get contraction. There we go. Again, I'm not going to say there's not some strange exotic material out there, especially with all the stuff that's being done today with composites, that there's something that behaves opposite of this. That's, again, not my area of expertise, so I'm not going to venture a guess there. But most common structural materials, certainly metals, this is what's going to happen. Temperature goes up, it's going to get bigger. Temperature goes down, it's going to contract and get smaller. Now, how much it's going to expand or contract is given by this formula. We used delta previously to denote the change in length, and the formula that we were using for an axial load was PL over AE. So same notation, using delta to denote the change in length, but the little subscript T there, just indicating this is due to temperature change, is alpha times delta T times L. So this is our new formula we're going to use here in this section and explain what some of these things are. Alpha is called the coefficient of thermal expansion. The units on alpha are going to be 1 over degrees Fahrenheit if we're working with English units, or 1 over degrees Celsius if we're doing SI calculations. But it is a material property. I've mentioned to you that table that's in the back of your textbook that has material properties. This is in that it's in that table, in the back of your text. One of the columns gives the coefficient of thermal expansion for each of those materials that are listed back there. In fact, let's see, I have pull up this we were looking at the other day, and I pointed out the modulus of elasticity, modulus of rigidity, yield strength, ultimate strength, Poisson's ratio. The very last column over here, coefficient of thermal expansion, that's alpha. And you see the values are times 10 to the negative 6. We got a. I don't know what that was. Anyway, those are the values, and these are all determined in lab. You take a sample of 2014 T6 aluminum, subject it to a known temperature change, measure the change in length, and then you can determine what that coefficient of thermal expansion alpha is. Right, so just point out that those values, if they're not given in the problem, they are given in that table in the back of the book. All right. Delta T there should be pretty obvious. So what delta T is, that is the change in temperature. So it'd be whatever the temperature is minus the original temperature. And it'll be positive if the temperature goes up, and it'll be negative if the temperature goes down. And finally, L there is the, this would be the original length at whatever that original temperature is. So the object sitting there at some temperature T naught, and it goes up or down. This is how we calculate what the change in length is going to be. All right, any question about that formula? Any of those terms in that formula? All right, then what we're going to do next is talk about, well, what if we combine what we have previously done in the sections prior to this, where we had an axial load, P, that caused a change in length, and we combine that with the temperature change. So if you want to get the total deformation due to, say, an axial load and a temperature change, you just add these together. So if you want to get the total, you just take what we did before, deformation due to the axial load P, and add the deformation due to the temperature change, or PL over AE plus alpha delta TL. If we've got a member, it's got an axial load and a temperature change. We want to get the change in length. We add those two together to get the total. All right, now, I mentioned a second ago that this idea, this term thermal stress, to me kind of implies it's stress caused by that temperature change. But it's actually not the temperature change itself does not cause any stress. It will cause a change in length, but it's actually a stress-free change in length. Where we get stress is if we constrain this particular object so that it cannot expand or contract due to the temperature change. So that's where we get stresses, is if a member is constrained. All right, so somehow or another we constrain it so that it can't expand or contract, so that it can't fully expand or contract. Again, if the temperature changes. Then it is subjected to forces that cause, go back to the name of this section, thermal stress. So it's actually the forces that are causing the stress, not the temperature change. So that's why I said it's kind of misleading when we say thermal stress. Also, just point out these are statically indeterminate problems. Indeterminate problem. Maybe a picture here might help. So if you've got some member not constrained in any shape or fashion, right? You apply some delta T to this thing. It's going to get longer or shorter, expand or contract, depending upon if the temperature increases or decreases. Right? You're going to get a expansion or contraction equal to alpha delta T times L. The stress is going to be 0. Right, so this thing's going to, if the temperature increases, you would get an increase in length. It's going to get bigger. But the stress is 0. Where we get stresses is if we constrain this thing. Maybe put this thing between two rigid walls and apply this change in temperature. In this case, it wants, if the temperature increases, it wants to get bigger, right? So it tries to expand, right? But the wall here pushes it back in, doesn't let it expand, and it generates this force. That force is what's actually going to cause stress. So in this situation, delta 0. It doesn't change length. It can't change length, right? It's somehow or another constrained on each end. So this thing can't get any longer or shorter. But the stress is not going to be 0, right? The stress here would actually be P over A. The axial, the stress due to this axial force P that's that's pushing this thing back in. Or if the temperature decreases, it tries to contract and get shorter. The walls are pulling back out to prevent it from changing length. That axial force is what's causing stress. Right? That concept makes sense. Right with me? This is how we generate stresses due to temperature change, not due to the temperature change itself. It's due to the fact if we've got the object constrained, preventing it from expanding or contracting, it's what's going to cause an axial load, which results in a stress. All right, so any questions about the concept before we work a couple of problems? All right, then we'll do a couple examples, and again, you'll see the sort of the big moral to this story is if you've got a structure that's going to experience a temperature change, you really, really need to pay attention to if you've got any part of this thing constrained so that it can't freely expand and contract due to that temperature change. Because you'll see we can generate some really large forces, and as a result, really large stresses due to that. So let's try this one. Let's see if I can draw this picture here. We've got it's a concrete slab. And so this is some kind of concrete slab we're looking at from the side. I'm gonna have my picture out of focus. Come back to me. All right, so we're looking at this concrete slab from the side, and this side of the concrete is fixed to the wall. Something is fixed to that side, but there is a little gap here of 0.125 inches. So a really small gap between the end of that concrete slab and some other rigid wall, right, that would prevent it from expanding any further than that. The length here, L, is 20 feet, and this is at our original temperature of 20 degrees Fahrenheit. That's our initial temperature. When this thing is 20 feet long, is at 20 degrees Fahrenheit. We're given alpha, coefficient of thermal expansion for this particular concrete is 6 times 10 to the negative 6 per degree Fahrenheit. And I don't know if we need this or not. We'll see. I think we do. Modulus of elasticity, E, is 4.2 times 10 to the third. Those are KSI. Okay, so those are the material properties for that particular concrete. Coefficient of thermal expansion, or modulus of elasticity. So we're actually going to do two things here. First part, part A here, we're going to try to find the temperature to just close the gap. In other words, at 20 degrees, it's sitting like 0.125 inches from this wall. What temperature is going to cause this concrete to expand so that it's just about to touch that wall? Okay, it just closes the gap. And then the second part, for part B, we're going to find the compressive stress if the temperature goes up to 110 degrees Fahrenheit. So obviously we're going to see that 110 is more than enough to close that gap. If depending upon what we get for part A, if the answer to part A is 120 degrees, then the answer to part B is 0. Right? If it takes 120 degrees to close the gap, 110 is not going to make it there. There is not going to be any stress. Right? It doesn't reach that wall. All right. So, any question about the problem setup, what we're looking at, and what we're trying to find? All right. So let's address part A. This should be really straightforward. Right? We just want to know what temperature is going to cause this thing to expand or get longer by 0.125 inches. That'll put it right at the wall. So delta T due to temperature change is alpha delta T times L. Right, we're going to set the deformation delta T equal to 0.125 inches. We know alpha, we know L. Solve for delta T. So 0.125 equals 6 times 10 to the negative 6. Delta t, that's what we're going to solve for. And the length is 20. Be careful with units here, because if you notice, these are inches, 20 is feet. So we need them both in feet, or both in inches. So I'm just going to multiply this by 12. And again, the reason for that is I want this to be in inches. This side is already in inches. And solve for delta t. And I got 86.8 degrees. These are degrees Fahrenheit, English unit. So that's the change in temperature. That's how much it's got to increase to make the concrete slab expand just to that wall. So if delta T is 86.8, then we're trying to find the temperature. We got to take our original and add that delta T to it. So we started out at 20. If I do my math in my head right, that would be 106.8 degrees Fahrenheit. So it's sitting there at 20 degrees. If that temperature goes up to right at 107 degrees, that concrete is going to be right at the wall. Right? Any question about part A to that? All right, so let's move then to the second part of the problem. All right, and note here that if we're going to 110 degrees, that's bigger than 106.8 degrees. So it's not only got to the wall, it tries to expand further, but the wall prevents it. So again, it wants to expand past the wall, but it can't, right? Because this wall here is rigid; it will not move. Right, so I do know from what we know about the deformation here. Again, the total deformation is going to be equal to the deformation due to the axial force that's going to be generated when it hits that wall, plus the deformation due to the temperature change. And that's got to be equal to 0.125 inches. Right? Since, again, 110 is bigger than 106.8, it's going to get to the wall, but it can't go any further. So the total deformation is going to be 0.125 inches. Now, sort of I don't know, might help sort of visualize, what's actually happening. If if you had this concrete here, and there was, say, if there was no wall actually there, when we apply this temperature change, this thing wants to go out past that where the wall is. This would be where the wall would be. This thing would expand out some distance, alpha delta TL, and since 110 is bigger than 106.8, it would go past the wall. It would go further than 0.125 inches. Right? But we do have a wall there. And so what happens, right, if you actually have this wall here, right, it's only going to go that far. Right? What happens is once it hits that wall, it tries to expand out further. We're going to get this force P that basically pushes it back in. Right? And how far it gets pushed back in, that's our delta P. You want to think about it like that, may help visualize what's actually going on. What I didn't write this down, but delta T would be what? If T is 110 minus, we started at 20, that'd be 90 degrees. Is our delta T. All right, so everybody with me? Understand what's happening here is the temperature increases 90 degrees. The concrete wants to expand out past the wall, but it can't. It hits the wall. As soon as it hits the wall, as the temperature continues to increase, it's going to push harder on the wall. The wall is going to push back, right? And that's, we get the delta P, we get the delta T, and those added together have to be equal to 0.125, because we know that is the deformation of that concrete. So let's, delta P here, I know is PL over AE. Delta T, that's my alpha, delta T, L. And those two added together, got to add up to 0.125 inches. Now, we know most everything here, right? We know we started out with 20 feet. We know delta T is 90. We know alpha. Again, we know L. We know E, that was given. But notice here, we don't know what the cross-sectional area is. Right? If we knew what the cross-sectional area was, we could solve for P and get that force here that's pushing on the concrete. But it's actually, for this problem, since if you go back to what was actually asked for, right, it asked for the compressive stress, not the compressive force. Well, the stress is P over A. So just make note here that sigma is P over A. So rather than if we were given that area, we could solve for P and get the stress that way, but we're not given area, so we can't find the axial force P, but we can find the stress. Right, so I'm going to replace that P over A with sigma times L over E plus, I'm going to go ahead and put the numbers in here. Let's go ahead and put the numbers in. So sigma for P over A, the length, 20, again, times 12 to get inches. E was 4.2 times 10 to the third. That's KSI, but it's okay. We can leave it. If you want to leave it in KSI, our stress is going to be in KSI. So whatever units you use here, that's going to be the units for your stress. So I got sigma times L over E plus alpha. Where's alpha? Alpha was 6 times 10 to the negative 6. Delta T was 90. Length, again, is 20 feet times 12 inches. That's equal to 0.125. And we solve for stress. I think it looks like I've got all my numbers in the right place. So, again, we'll skip going through the algebra. I got, it's going to come out negative 0.08, I don't know, 05 KSI. Note the negative here is indicating, what we pretty much knew going in. This is in compression. That concrete tries to expand out past the wall pushes back, and it's creating a compressive normal stress. All right. Any questions about this problem? All right, well, we're going to look at one more. I'll give you just a second if anybody, I'll ask. Anybody, do you need a second more to finish copying down anything, or can we go to the next problem now? Say that again.
I'm still copying.
Okay, let me know when you finish. While we're sitting here for a second, just bring up something kind of related to this. If you've noticed, when you see if you got a concrete sidewalk being built, or interstate sometimes is concrete. Especially if you notice this, if you've driven down a concrete interstate, you get and it's because of the little gaps between the concrete slabs. This is exactly why those little gaps are between the concrete slabs in the highway or on the sidewalk, is so that when the temperature changes, that concrete has room to expand so that you don't get that compressive stress. Right? It doesn't hit the next slab and you don't get that compressive force, which causes the stress. All right, we're good now?
Yes, sir.
Okay, let's work another. This one, kind of similar, a little bit different. Let's see again. Well, let me draw the picture first. I think we'll start with that. Here we've got this member is actually made of two different materials. This is brass. It's 3 feet long. Over here we got aluminum. It's 2 feet long. And here at A, it is fixed. It is rigidly attached to something at A, and we'll call this B, and we'll call this C. So same thing over here at C. It is attached. It's not just resting against the wall. It is fixed, attached to that wall. And we got some material properties. The cross-sectional area of the brass is 1.75 square inches. Modulus of elasticity, 14.6 times 10 to the third KSI. And alpha, 9.8 times 10 to the negative 6 per degree Fahrenheit. So that's the cross-sectional area, the modulus of elasticity, and the coefficient of thermal expansion for the brass. And over here for the aluminum, we're told the cross-sectional area is the same, 1.75 square inches. Modulus of elasticity, 10.6 times 10 to the third KSI. And alpha, for the aluminum, 12.8 times 10 to the negative 6 per degree Fahrenheit. Right? So we're told that there is no load or force in this structure when we'll call it T1 is 50 degrees Fahrenheit. And we want to find the force in each of those let's say each section. When T2 is 120 degrees Fahrenheit. Right, so this structure sitting there, there's there's no force in it whatsoever when it's 50 degrees. But the temperature goes up to 120. So we got delta T here is 120 minus 50 is 70 degrees. So the temperature is going to increase 70 degrees. Like that previous example we looked at, right? This member wants to expand and get longer. Right? Temperature goes up, it wants to expand and get longer, but it can't. Right? It's being constrained between these two rigid supports. But as it tries to expand, those supports push it back in, generate this force. That's what we're trying to find. We're trying to find what is the force in the brass section and the aluminum section at that temperature. Right? Again, sort of pictorially, if you will, what we've got is we've got this section here, or this member. Right, so if we didn't have a wall over here on this side, this thing would want to expand out some amount delta T. Right? But we, in reality, do have a wall here, and so that prevents it from doing so. So this wall is generating that force that's going to push this thing. We got this compressive force P here. It's going to push it back in some amount. So the total deformation is going to be zero. It cannot get longer or shorter. Now, this amount that it wants to expand, here, unlike the first problem or the previous problem where we just had one material, we had just concrete. Here we got two different materials. They're going to expand at different values because two different materials have got different properties. Right? So this is going to be due to the brass plus the aluminum. So we're going to have to break it up and get, for each section. Same thing for deformation due to that axial load P. Right? It's going to be due to the brass, and we'll also have deformation due to the axial load from the aluminum, because again, these two different materials behave differently. So a little bit different than the first problem where we just had one material. Here we got two different materials. Now, we know from equilibrium, and this is mentioned, these are statically indeterminate problems. If you look at this, and this is the brass, and this is the aluminum. As this thing tries to expand, right, you're going to get that constraint rigid wall at A is going to push back in. Right? That's going to be some force, we'll call it P brass. Likewise, this rigid wall here is going to push in, push back, and we'll call this P aluminum. Now, the fact that there are no other forces acting on this thing, if it's in equilibrium, some forces got to add up to zero. Well, if we only have two forces, they got to be equal to each other. And so this just tells me that the force in the brass is equal to the force in the aluminum. All right, and I'm just going to call it P. So we're just dealing with one variable here. This compressive force P here. Now, if you had an additional force acting on this thing, this would not be true. Say, if I had some force, acting here at B, like an applied load of, 10 kips or something, then these aren't equal, right? They would, the force in the brass, the force in the aluminum, and that applied load would all add up to zero. but we would not know and we could not say that the forces were the same. It works out this way for this problem because those are the only two forces we have. Right? Is that clear? Everybody understand? That's not going to be the case all the time. If you had something else acting on it, that wouldn't be true. All right, so that's what we know from equilibrium, but that's not enough to solve for that force. Right? We got one unknown, right? But we don't have any other equations that we can apply equilibrium-wise. Some of the forces in the y equals 0 doesn't tell us anything. These two forces are collinear, so sum in the moments doesn't tell me anything. So that's all we got from equilibrium is that I know those two are equal. We can solve it though if we also use what we know about deformation. Right? I know the deformation due to the temperature change plus the deformation due to the axial force P, it's got to be 0. This thing, the total change in length is 0. It cannot change. It starts out 5 feet long. We apply this delta T, it's still going to be 5 feet long because it's constrained where it cannot expand. Now, we'll mention that does not mean that the brass stays 3 feet long and the aluminum stays 2 feet long. Those can and will change length, and if we weren't asked to find it, but you could, after we find this force, you could go in and calculate what the new length of the brass is and the new length of the aluminum. It's not going to be 3 and 2. One's going to get longer and one's going to get shorter. But the total is still going to be 5 feet because it's constrained. It can't change length. So what we're going to do is, again, the deformation due to the temperature change. We're going to get alpha delta T L for the brass plus alpha delta T times L for the aluminum. Right? Go back to what I talked about earlier, that total deformation due to temperature change. We got to break it up and add those two separately because we got different materials. Same thing for the deformation due to the axial force P. We're going to get PL over AE for the brass and PL over AE for the aluminum. And when we add all those up, we're going to get 0. And so we know everything here except P. And then we can solve for P. Now, if these two weren't equal, we'd have P for the brass and P for the aluminum. We'd have two unknowns here. But we'd also have another equation up here that we could use. We could get there. Now, before I put the numbers in here and solve this, I want to ask, take a poll, and there's no, right or wrong answer. I'm just asking for a guess. Given this problem, where we've got this brass and aluminum bar between these two rigid walls, temperature goes up 70 degrees. What do you think that force is going to be? How much force is going to be generated by increasing the temperature 70 degrees? Now, I'm asking for guesses. You can just type in the chat, or you want to unmute and speak up. I'm asking. We'll get at least 3 guesses, and then we'll go on. So the quicker y'all guess, the quicker we can finish. What do you think our force is going to turn out to be? Approximately a lot. Now I want a number. Give me a number in pounds. I got one guess. I got 350. I'll write them down here. So 350 pounds. I got a 5,000 pounds. All right, I need one more guess. 70 pounds. All right. Somebody else wants to add, that's fine, but I got three. I asked for three. All right, well, let's plug in the numbers and see how much force is actually generated by increasing our temperature 70 degrees here. So let's put in the numbers. We got 9.8 times 10 to the negative 6. Delta T was 70. Length, the brass is 3 feet long. Here we need to multiply it by 12, get inches. Alpha for the aluminum, 12.8 times 10 to the negative 6. Delta T is 70. And it's 2 feet long. So multiply that by 12. Plus, again, the force in the brass, the force in the aluminum are the same. We just call it P. The length, 36 inches. The cross-sectional area is 1.75. And E, this is KSI, so it's up to you. If you want your answer in kips, you can leave it in KSI. If you want it in pounds, change that to PSI. Multiply by another 1,000. And then for the aluminum, we got P times 24 inches long. Area is the same, 1.75. And E is 10.6 times 10 to the third. That's KSI. All that adds up to 0. Now, I think I wrote all the right numbers in the right place, but if somebody sees where I wrote down the wrong thing somewhere, please speak up and say something. All right. So now the drum roll, big reveal. And remember, this is going to come out in kips, and it's going to be negative because remember this is a compressive force. Try about 17. We'll just round it to 0.09 kips. That would be 17,000 pounds, a little over 17,000 pounds of force. That is a very significant large force generated by 70-degree temperature changes. I mean, there's lots of situations you could just about get that just due to the weather in the day here in Mississippi. But think of like a part in an engine or something that's running and heating up. Definitely, temperature is going to increase more than 70 degrees. So that's why I said the moral to this story is be very careful if you're constraining things that the temperature is going to change. You can get really, really large forces from not outrageous temperature change. Any question about this one? One other thing, somebody's still copying down. Hey, I mentioned, a minute ago about the interstate and why you see gaps between the concrete slabs. Well, something. Oh, yeah. I'm sure, Nathaniel, you would have got that. That was your next guess. You would have been right on it. If you're driving around, say like the bypass, Highway 82 bypass, when you drive under one of those overpasses, you may not have noticed this before, but you see this big concrete column, that's your car driving across. Well, if you look at the end of those, it's not attached, right? What you'll see, the road, there's actually a gap here, right? You're going to see this little gap. It's going to be resting on this thing, but you're going to see this little gap here. Ooh. Do it this way. So next time, if you haven't noticed or looked at that, as you drive, you go under that overpass, look and see that big concrete, it's steel reinforced concrete beam there. There's little gaps at the end. This is exactly why there's gaps in the end there. It's so that when that temperature does change, this thing has room, it can expand or contract, and you don't generate those large forces. Right? There was also, last thing, and then we'll stop. There was a picture in your book. Right, is everybody, I can move this now? Nobody said no, so I'm gonna move it. Let me see. I got the book here. We'll find that page. Here we go. This would be sort of related to what we were just talking about. This is, looks like, focus. Page 155 in your book. Where's that one? Focus one. There we go. But if you look at this picture, here's a picture of it's actually a bridge, and you see the little gap in there. That's why it's in there for. And so when the temperature goes up, that thing's got room to expand, so you don't get those large forces, right? All right, so any question before we wrap this up related to temperature change? I'll put this back here, like my picture. All right, no questions? All right, so tomorrow we're actually going to change gears. Literally, we're going to start chapter 5 when we're going to start talking about twisting things. Chapter 4 has been about axial loads and axial stress. Chapter 5 is going to be about torsion, torque. We're going to twist stuff. That's what we'll start talking about tomorrow. If anybody's got questions about anything, same invitation as always. You can stick around. In a couple minutes, I'm about to stop recording, but if you want to hang around and ask me questions, I'll be glad to stick around and help you. So otherwise, I'm stopping recording.